Hello there YouTubers, it's been a long time, but I'm back. I'm your host SuperDave001 and welcome to my tutorial series on OpenGL. Now, where did we leave off? Well, we got shaders working last time, I believe, and we created this. Well, you might have used your own textures, but yeah. We created this and we rendered it using the shader pipeline in OpenGL. So, where are we going to go next? Well, you know, I said last time, why on earth are you wasting your energy making all this when it's only just going to do the same stuff? It's not. I'm going to show you how to really use shaders, and by giving you an introduction to lighting. So, how does lighting work? Well, the first thing is we're going to need to, when we render this, we are going to need something else. We are going to need something called the normal. Now, right, not notepad. Okay, paint.net. Give it a second. Okay, hurry up now. Man. See which one loads first. There we go, paint. Paint.net seems to be on a go slow, never mind. So, the first thing we'll need is a normal. So, what is a normal? Well, say I had this shape. This is a terrain or something like that. One large model of terrain. And there's a mountain, and yeah. So, the normal at any point is a line that is perpendicular to that point. If I can remember how to get the line tool. There it is. It's the point that is perpendicular to the line at that point. So from here it would be about here. It basically means that it's 90 degrees away. So you could draw that as a right angle if I've drawn it right. And from there that would be a normal. And from there that would be a normal. So you get what I'm doing, but you have to define these in the code. And there's paint.net. Bye bye, you were too slow. Don't worry, this is really easy to do. You just have to know the shape. So, I need a second to think. So it's GL normal 3F, and this has three arguments, which are the X, Y, and Z of the normal. So it appears I'm drawing this shape along the X and the Y axis. By the looks of it, I can't really remember because I've not done this for a while. So the normal is going to be along the Z, and I think it's going to be 0, 0, 1. So yeah, that's the normal setup. But we're going to need that in lighting calculations later, and you'll see why. You'll know by the end. Now, I will warn you now, this video may contain maths. A significant amount of maths, so... But don't worry, don't be scared by it or anything, it's fine. So, that's... Adding in the normal is all we need to do in this bit for now. Might need to add in... Might need a few uniforms later on down the line, so... For now, let's go into the vertex shader. And we need a new varying variable, which is avec3, and that's normal. And this is easy to do. That is normal equals gl underscore normal matrix star gl underscore normal. And that's the normal. And in fact that's the whole vertex shader done, I believe. So, varying vec3 normal. I'm going to call that T-color for now. And I might put this into a new function. It will return a vector3, and that is calculating. So this is a function which will return a 3-component vector for the light color. And in fact I'm going to put that into there. And just to check it still works, just to check I've not done anything stupid this early on. Compile. Run. And yeah, believe that works. So now we have to calculate the lighting. To do that, you're going to have to understand a little bit about how lighting works. So with lighting, there are three different types of light which we'll be simulating. And I need a diagram. So if we have a plane, very straight plane like this, think of this as one triangle or something like that. So we have this plane here, and we have a light, which is that. We also have, if I just draw it with a brush, we also have an eye, like so, and that's looking at the scene. And the normal for this object is, I'll draw it in red again. The normal is there. So there are three kinds of light that we're simulating. The first one is specular lighting. Is there any way of doing dotted lines in this? Can't see any. I'll do these as grey light. No, oh, for goodness sake. I'll do these as light grey lines so that you can barely see them, and they'll also be wafer thin. So the first kind of lighting is specular. This is light which goes from the light source, it goes down here, and it bounces pretty much straight into the eye. Although we'll allow for a small area like that. But this is like you'd see, this is the shiny spot in an object. You'll see what it looks like later on. It's the especially shiny area from the direct reflection. Think of looking at the sun in a puddle. Say that as an analogy. So that's specular. The next one is diffuse, which I'll do with the thicker line. Oh, stop doing that. And this one, it goes down there again, but this time it can come out in any direction along here. And this will be fainter light. Won't be as bright, but it'll still be pretty visible. And that just goes all over the place. And finally, edit colours. Oh, ignore that. And the final type of light's ambient, which is all over the place. So that's how the different types of light work that we'll be simulating. Oops. No, I don't want to save it. Ignore that. So yeah, the first one we're going to simulate is, actually before we simulate them we need more uniforms. We're going to pass in a lot of uniforms here. So because the light needs a certain amount of ambient emission and the object needs a certain amount of ambient as well. So we need a lambient. Need to do the same thing for diffuse and specular. Diffuse, specular. Diffuse. Oops. And then we'll have a uniform float for shininess. And if I can get that back up. Shininess is basically just how much the specular light spreads. It'll be brighter if I set the shininess high, but it'll only affect a thin area. If you say it too high, if you say it too low, it just starts acting like diffuse. But yeah, and then after that is uniform vec3. Actually, I don't need to do it like that. And I'll do the same thing for the object's material. And I also need one more uniform. The light position, because we need to know where the light is. Although I think the light at this point the light's going to be relative to the player, so light pos of 0, 0, 0 is going to be where the player is, not that it's a player, it's just a camera, but that's where the light's going to be. So we'll fill them in later, but for now we need to create some more things. Let me just look at my cheat sheet. It's slightly more difficult to read than it should be, so I apologise. So first of all, we're going to simulate ambient light. So this ambient is going to be the resultant ambient after all the massive amounts of calculations we're going to do to get it. So what do you do to get ambient? You take the material ambient, multiply it by the light ambient, and then multiply it by the texture. I know, hard, right? There are better ways of doing it, because with the diffuse and specular we're going to calculate a contribution which will be multiplied at the end. Like that, making sure that I spell it right, don't want to offend anyone. So we're going to have the contribution on the end with the others, but with ambient we don't do that. It can be done. If you want to do that, look up ambient occlusion, because that calculates a contribution, and especially screen space ambient occlusion, which is designed for being done in real time. And it's a very good looking effect, but maybe on a later tutorial. But for now, that's too difficult. So that's how you get the ambient light. Now we need to calculate the vector from the surface to the light. And surf to light equals normalize light pos minus position. Wait, do I even have a position? One sec, let me think about this. Okay, it turns out I could do with a position, and that's going to be a varying variable. Oh, for goodness sake, my typing. And so the vertex shader wasn't done in the end. I might put this before them. So position equals vec3 of gl underscore model view matrix times gl underscore vertex. So yeah, if you're wondering what model view matrix is, it translates it to its position in the world relative to the camera. But that's the story for another time, because that is, we'll get into what the matrices mean later, but for now it's just GL model view matrix times GL vertex. But you have to make that into a vec3 because the vertex by default is vec4. And so yeah, now that we have a position, let's put it in here. And yeah, so now that we have a position, we can do that calculation without problems, and then create a vec3 called norm, which will be the normalized normal. So if I haven't told, I'm not sure if I've told you already about normalize. I don't think I have. But what it does is if you start with a vector of length up, because vectors have a length and a direction. So yeah, it has a length, which is L, and then it also has a direction. Normalize basically makes the length equal to 1 by dividing each component by the length. So it makes the length equal to 1, so you can just use the vector to get the direct as another form of direction. So yeah. But because of the way interpolation works, when you take the normal, that's not necessarily normalized, so you have to normalize it yourself. Because otherwise it will completely glitch out the light. Well, it might. I'm not sure why it does actually, but it does glitch it to an extent at least. So yeah, there you have it. And then the next thing we're going to do is calculate the diffuse contribution. Our first contribution. That equals, and I'm going to have to explain this in a second. So it equals the largest value out of 0 or the dot product of normal and surf to light. So, oh, for goodness sake. So, hold on. I'll explain that. Here you have your surface. Here you have poop. In red you have the normal up here. And over here is the light. So, what is the dot product of the normal and the surf to light? Well, the normal points up there, the surf to light points up there. The dot product, mathematically it's a cosine function, which is trigonometry, but all you have to think of it as is a measure of similarity between the two. So if the normal and the direction to the light are the same, then that's going to equal 1. If the normal and the direction to the light are perpendicular, then that's going to equal 0. If the normal and the direction to the light are completely opposite, that's going to equal -1, and then 0, and then back up to 1. So yeah, it's a measure of similarity, but to avoid bugging out the lighting, we don't want negative values for ones under here. So if it's under here, then we say it equal to 0 by saying that if it's less than 0, just use 0, and that's what this max statement does. It picks the largest of these two values, and that's how diffuse lighting works. And so then vec3 diffuse equals the decontribution times the texture diffuse times the material diffuse times the light diffuse. That's not light, that's L, before I get that wrong. So that's diffuse lighting done. Now we need specular. This one's a little harder. We're going to need another vector, and that's going to be the surf to view vector, and that is normalize minus position. Of course, that's surface to the camera, not camera to the surface, so you have to subtract the position. Because in this state, because we'll multiply by the model view matrix to get that position is going to be relative to the camera, so the camera is going to be at the origin, right down here. So the object's going to be up here. And rather than drawing a ray, I was going to say, I'm not used to paint. So instead of drawing a ray that way, you draw the ray to the view, because that's what we want. Okay. So yeah, there's the surface to the view vector set up. Now we need another vec3. How do I do that? There. And that's going to be reflection. And that is going to be equal to the reflect function, which reflects vectors like a mirror would. And that is reflect minus surf to light and the normal. So what that does is, again, if we have the shape here, I really didn't know to keep redrawing this, and you have the normal here, and you have the light up here, which is the sun. If you go back to that, this is surf to light going up here, and it has a direction, and it has an angle equal to. Whoa, okay, I can't draw curves either, it appears. Or maybe I can. There, that has an angle equal to x, just call it x. But what reflect does is it creates another vector going out this way. It's reflected about the normal, in this case. And this one also has an angle of x. So the angles are the same, it's just like reflecting from a mirror, which is handy. It's a handy function because that's quite hard to do yourself. There's also a refract function for if you want to do glass, but again that's something for a later date. So now we need the scont, which is equal to, which is the specular contribution is equal to, and you're not going to like this, pow max no dot. So it's equal pow max 0.0 dot surf to view, and the reflection to the power, so that's shininess. So you're not going to like, and I'm sure you don't like that. So let's break it down. Does the dot product of, so when you have this reflection, let's make the eye, I don't know, pink. It's got skin, so I don't know, pink. Let's put the eye there. So it's a measure of similarity between that reflection vector and this vector here going to the view. So the more similar they are, the higher that value. And the pow thing, the pow determines the fall off. And you can look at it yourself and think about, you have to think about how the power function actually works. Because it's basically like doing d, which is what I worked out already, to the n, which is the shininess. And the higher that number, the more a graph of it would spike like that, and that's going to look wrong. So that's the the more it would spike up, the closer it gets. So again, that shrinks it off, so it falls off much faster. So you'll see it in action anyway in a second. And so now we can calculate a vec3 for specular, which is equal to the scont times the material specular multiplied by the light specular. Now you may be wondering why we're not multiplying it by the texture. It's because when you look at objects with specularity in real life, they don't tend to think of a polished wood object, something like that. Think about how the shiny areas of it don't necessarily have the colour of the object underneath. So it just works, trust me. And now we're going to return the colour, which is ambient times diffuse times specular. But now I need to fill in some uniforms, and that is the ambient, diffuse, the specular, the shininess, the ambient, the diffuse, and the specular. Now I'm going to have to guess at these values because I don't really know them. Simple shader set uniform float 3. This is going to be ambient, and I'm going to make it 0.2, 0.2, 0.2. These are just guesses. They're probably better values, but I haven't thought of them yet. So ambient, I'll diffuse specular. I'm going to make this one equal to 0.6, 0.6, 0.6, and this one equal to 0.8, 0.8, 0.8. Feel free to experiment with these values. In fact, feel free to do whatever the heck you want. I'm not going to stop you. Just don't hold me responsible if it gets you in trouble. And so set the shininess, I'm going to say equal to 50 for now. Now I'm going to do the same. I'm going to leave these values the same for the material as well. As ambient, diffuse, and specular. And what's that? Something's rubbing there. It's rubbing against my jumper, I think. Sorry about that. And then simple shader dot set uniform flow 3, because it's no good having that if you don't know the light pos. And for now we're going to leave it at 0, 0, 0 because that will put it on top of the player. I think I've named all those variables right. That would be handy. So yeah, that's the variables set up for this. Am I ready to test it, or have I done something horribly wrong? One sec, just cables. Yeah, light pause. Let's give it a test. See how badly broken it is. Oh, it's not doing anything. That probably means that the shader didn't compile right. Right. Let's go into the bin folder, the debug folder. This is where the std out thing is. Ignore that. That's printed out the source code. Why is it printing out a load of babble? I have no idea. Vertex shader compiled to run on hardware. That's good. Fragment shader. Haha. As per usual, bugs, bugs, bugs. Let's fix them. Feel free to laugh at me for a second while I try to fix this. Right, I'm going to have a look at it. When I find out what it is, I'll show you. Okay, bug number 1. I think this might help with one of the bugs. Okay, let's look. So I accidentally left that as a vector 4, which when you can't really multiply with the others. Actually, I might make that a vector 3 and set that equal to dot x, y, z. If you're wondering, I am famous for not getting shaders working the first time. Takes me a few tries. Back in a sec. And second bug, there is no such thing as T-diffuse. T-diffuse is actually just T-color. And I called it T-color because T-diffuse would imply I'm just using the texture for diffuse, which I'm not. So yeah. Surface view reflection. See if it works now, because I have a feeling that 2 of the bugs might have just been the same one. Nope. Let's have another look. Yeah, line 43. Can't convert from 3 component vector. Oh, of course. GL frag color wants a vec4. This is a vec3, so set that to that and add in a 1. So it get. Oh, that would have created another bug. That's a vec4. Just again leaving the alpha at 1 because I'm not dealing with alpha transparency at the moment, because that gets difficult. And will it work? Ugh. For goodness sake. Okay, now it's not rendering anything. Let me have a look at this. I'll see you in a moment. It's doing something. Still not fixed it yet, but it's doing something. I've changed up some of the variables. I've tried to make things brighter so in the hope that it makes it more visible, but look at it. It'll come up. There is something lighting going on. I'll be back in a moment when I've explode a bit more. You know what, I'll fix it in a minute. For now, I'm going to try to show you attenuation. Oh, and I've removed that, by the way, just so you know. I've removed I'm going to attempt attenuation. And what is attenuation? Well, attenuation's simple. Think about it. Attenuation is light getting fainter with distance. And as it turns out, I've just been looking up about that in physics at school, but that's beside the point. So you look at the light up close, and it is really bright. If I can get a circle, it is uber bright. But if you double the distance, what? Don't ask me why it's done that. Paint's stupid. I never use it normally. If you double the distance, it gets a quarter as bright. It seems a lot fainter. Think about looking at a candle a long way away. That's the only reason stars don't blind us. So yeah, that's what we're going to do next. And for now, rather than passing it as a uniform, I'm just going to call it a float. Atfac. That's going to be, for now, 0.05. I can change that later. So we need a float for dist equals it's the length of the position minus the light's position. Still works ish. I don't know why it's been like that, but it only seems to work when it's on the flat. It's weird. Oh, I know exactly why it is. Silly idiot. They should be pluses. Round of sarcastic applause to me. Let's put these back to 0.2. Set these back to what they were before. My apologies there. I accidentally paused the video. Didn't do much in the time, so you probably didn't notice it. I apologise for jabbering on about it then. 0.2, 0.2, get back. 0.2, 0.6, 0.6, 0.6. That looks better. How do you like that? Oh, and I also moved out of my... I kind of... Where is it? Yeah, I changed that to -8 from -5, so I'll put it back just so you can see the light up close. Look at that, that is cool. So, Atfac. Interesting name. So that's the distance. And to calculate the attenuation from that, you do 1 over, because it's the inverse, we don't want it to get brighter with distance. That would be terrible. So it's 1 over at FAC times dist squared. In other words, dist times dist. And to apply it, you multiply everything by attenuation. And so you end up with this. I know what you're thinking, yes, it's the same. If I was to move further away from this, though, it would change. Or if I was to move closer, in fact. I believe I have another thing open. Oh, that's not important, actually. That's not going to help. So yeah, that's basically lighting done. But one of the cool things with this sort of system, though, is that you can change the colours of the light. Feel free to have a mess around with this. I'm gonna just quickly do it by halving these. So then you end up with a pink light. You can change the colour of the light, you can change the colour of the material, it's so powerful. I think I need more than 0.6 on that, I might change that to 0.8. Just to brighten things up a little. Because at the moment it's pretty faint. So yeah, that's basically lighting done. Oh, have I left the ambient pink? Yeah. Never mind. Come on. Have I still left the ambient pink? How? What? It's literally just undone that. I could swear I just did that. Never mind. Now you may be wondering why the texture's not drawn on the back. The answer is I don't know. That's not a problem though, because usually with graphics you only draw from the front, and quite often you stop it drawing from the back anyway to optimize things. Yeah, that's basically lighting. But just because I'm so kind to you, I'm going to show you what happens when you change the shininess. If I change it up to 300 for instance, you'll see the shiny area becomes a tiny spot. And if I change it to 2, let's see how bad this is. Yeah, it becomes an absolutely huge spot. So, yeah. I often use 50 as just a general value. Yeah, so that's lighting once again. Thanks for watching everyone, and it's good to actually be back making these tutorials. I've been pretty busy lately with A-levels and other projects, so I've not really been able to make tutorials. So yeah, so thanks for watching, and I'll just leave you on one more thing. Actually, no, wait. No, I won't actually, because again, I tried it before and it won't show it, and I can't be bothered with it. Never mind. Thanks for watching, and what we're doing next time, I think it might be good to do a first-person camera sort of thing, so that you can move around. So you can move around the scene and look around from every angle, because that's always nice. Yeah, thanks for watching, and enjoy programming, and I'll see you next time.